Hey there, welcome to the presentation of our research work, HANSAX, towards heterogeneity agnostic and multi-level explainability for deep graph networks. Let's start with introduction. We all know that graph is a powerful data structure that encodes complex knowledge, including topological structure and feature information. Deep graph networks are proposed to combine node features and graph topology such that they become state-of-the-art techniques on both heterogeneous graph and homogeneous graph. And the figure shows an example of a heterogeneous DGN predicting research areas of our target author, John, based on her citation network. In this graph, we have three types of nodes: the author node, paper node, and conference node, while research keywords are encoded using bag of words as node features. Author and conference nodes are labeled by their areas, such as database, artificial intelligence, and information retrieval. In this example, the DGN correctly predicts that John is a database researcher. However, these models still serve as black box predictors, which hinders them from becoming reliable tools with transparent decision-making mechanism. So extensive research efforts has been devoted to explain the DGNs, which allows users to interpret the reasoning behind the predictions and help experts to examine the network before it takes any real-life service. Specifically, explaining a DGN is to answer the question, which part of the input causes the model to make such a prediction? In this work, we aim to explore the heterogeneity agnostic and multi-level explainability of DGNs. First of all, heterogeneity agnostic means the explainer can be uniformly applied on both homogeneous and heterogeneous graphs. As the two types of graph remain irreplaceable in practice, having a heterogeneity agnostic explainer is natural and inevitable. Moreover, such an explainer offers a one-stop answer to all questions from an end user, such as which type of graph this is, what kind of model, and why this prediction, and etc. So it is highly user-friendly. On the other hand, a reliable explainer should also be multi-level, meaning that it should give both topological and feature-level explanations. Firstly, this is to fully explore the knowledge enclosed in the graph data. Secondly, topological level information alone can be misleading. In this example, we know John is a DB researcher, but if we check out the graph structure here, John published a paper at CIKM, which is a information retrieval conference. She also collaborated with an AI researcher and had one publication at AAAI. The topology does not give any clue that John works on database. On the contrary, we see that in the node features, John's keywords include representative ones for the DB areas such as pruning and efficiently. Moreover, her published paper have largely explored DB techniques such as factorization. That's why we need multi-level explanation. In conclusion, DGN explainers should be both heterogeneity agnostic and multi-level to ensure it's adaptable and reliable. In general, current studies are either matrix-based or causality-guided. Metric-based methods use human-defined metric to quantify explainability, but there still lacks a comprehensive and object unified standard. On the other hand, the causality-guided method adopts a Bayesian network to model the dependency of the prediction on the input, which avoid computing explainability. However, it fails to preserve the connectivity of selected important nodes, which violates the message passing principle of DGNs. To address all the drawbacks discussed, we propose HANSAX in this work, a heterogeneity agnostic and multi-level explainer that is causality guided. Let's go to the background. In explaining a DGN, the model is pre-trained and fixed. Any internal information such as parameters, gradients, or losses is not allowed, while the explainer can query the prediction score for multiple times. The reason is that DGNs are usually black boxes, and their internal structure is not accessible in real-life applications. Bayesian network is introduced to the DGN explanation because as a graph-based model, It allows direct and natural adaptation to this task by treating nodes in the input graph as random variables. Then causality between a DGN's decision on the input can be unveiled as dependencies of the prediction variable on the input node variables. Furthermore, Markov blanket is employed to be the criterion of explanations, as the entire Bayesian network is not necessary and the only critical part of the input is of interest. By definition, a Markov blanket is a subset of random variables, such that the target variable is independent of all the other variables conditioned on the blanket. In our problem, the Markov blanket of the prediction contains all dependencies of the model's decision, which is independent of any other variable outside the blanket. Aiming at multi-level explanation, we treat each feature on every node as random variables, and then the problem becomes to find a subset of entries in the feature matrix that is a Markov blanket of the prediction. The methodology is designed in this way. Markov blanket of the prediction is learned by first collecting a group of samples, then the blanket can be searched based on the observed data. We also have a module to generate factual and counterfactual explanations, which will be introduced later. The sample generation step is to generate pairs of perturbed inputs and the corresponding prediction score. Each feature variable records if the underlying feature is perturbed or not, while the prediction variable can be either maximized, minimized, or just in the middle otherwise. We adopt the classic grow-shrink algorithm because it has provable correctness. In the growing phase, the algorithm starts with an empty blanket and scans all random variables. If there exists one that is not independent from the target condition on the current blanket, we add it to the blanket. And then in the shrinking phase, it just removes the variable which the target is independent of conditioning on the others in the blanket. Complexity of GS algorithm depends on the order of conducting conditional independence test. In the best case, where the Markov blanket is found at the beginning, the conditioning set will not grow, then the complexity is OZ times D. Z is the number of variables and D is the sample size. However, if the Markov blanket is found at last, the conditioning set keeps growing, resulting in a complexity of O2 to the power of Z times D. There is no general rules for best case because Bayesian network is complex and random, but we do have some opportunities in our problem. We can first screen out some variables, then properly order the variables for conditional test. Finally, an elegant stop condition can also help. Variable screening step is to screen the variables that are marginally independent from the prediction. It can be proved that these variables are not in the Markov blanket, and marginal independence test is much more computationally cheaper. We term the set of marginally dependent variables blanket basket because it plays the role of a container that holds the blanket and the blanket never oversteps its capacity. Next, we will build a surrogate network to search for a Markov blanket. This example also comes from the DBLP dataset. Treating features as random variables, we will have the original Bayesian network shown in the green box. The first step is to introduce variables in the blanket basket to the surrogate network because the basket contains all causes of the model's prediction. The second step is to introduce synthetic variable for vertices and transfer the network structure from the original network to the surrogate one. Synthetic variables are used to combine the causal effect of multiple variables in local structure of large-scale Bayesian network and proven to be effective for reducing combinatorial explorations. Lastly, we apply the idea of causal independence here and introduce contribution variables so that we can have a realization rule of vertices by treating them as convergence variables. Now that we have the surrogate network, the lemma here states that under certain conditions, a Markov blanket of the original Bayesian network can be recovered using a Markov blanket in the surrogate network. We invite you to check out this lemma and the proof in our technical report. We also have some other nice properties that savers the number of conditional tests on feature variables if the underlying vertex is already tested independent. Notice Markov blanket may not be unique, so we define necessary variables as those that are in every Markov blanket. In the setting of our problem, we also further term the vertices associated with necessary variables as necessary vertices. Since the explanation subgraph must be connected, we assume every vertex that is necessary is connected to the target by other necessary ones. This assumption means vertices carrying critical neural message flow are all necessary in determining the model's prediction. Subsequently, a graph traversal strategy can be employed to properly order the variables for the conditional test, and an elegant stop condition can be developed. Specifically, the stop condition is like this. If we have a structure that contains the target node, then if there are no variables in the neighborhood, that a prediction is not independent of condition on the current blanket, we stop the growing phase. It is proof that the rest of variables are for sure not in the Markov blanket. The workflow of HANSX is like this. We initiate a blanket with feature variables on the target nodes that are in the blanket basket first, and then dynamically expand the explanation by adding variables from the neighborhood of the current structure by testing the vertex variable first, and then later the feature variables until the stop condition is reached, and then we shrink the blanket. We have the theoretical guarantee that a Markov blanket of the prediction will be found using this workflow. Thanks to the shrinking phase, we can prove that vertex variable in the output are direct parents of the prediction, and maximum likelihood estimation can be used to learn parameters of the prediction. When the prediction is maximized, we have the factual explanation, meaning that given this piece of information, the model is most confident about its decision. When the prediction is minimized, we have counterfactual explanation, meaning that without this piece of information, the model changed its decision. Correspondingly, we measure the factual effect and counterfactual effect of the output. For factual effect, we keep only the explanation and remove other information from the input and check how confident is the DGN when given only the critical part. While for counterfactual effect, we remove the explanation parts and see how much does the DGN's confidence drop without the critical part. In the following, we present experimental results. We compare our method to 8 competitors on 3 real-life datasets, among which DBLP and IMDb are heterogeneous graphs, and MUTEC is a homogeneous graph dataset consists of molecular structures. We set the sample size to be several times as large as the number of variables. Let k be the multiple, we tested k from 10 to 30 with a step length of 5. Out of the 5 tested value, k equals 15 gives the best quantitative results. Regarding effectiveness, HANSX outperforms all the competitors in factual and counterfactual effects using less information, meaning that our methods provide smaller set of features and nodes as explanation. We also give qualitative analysis by visualizing results on the DBLP dataset. We use the same example as in the introduction, where the DB researcher, John, has a misleading graph topology. We see that HANSX ignores the misleading structural information and finds critical features on the target node only, while the other explainers fails to do so. This shows our methods output precise and concise explanations. In conclusion, we propose a heterogeneity agnostic and multi-level DGN explainer that is guaranteed to find a Markov blanket of the model's prediction. The experiments on 3 real-life datasets show that our methods outperform SOTA techniques. Thank you.